Hello. This week we will be looking at hypothesis tests for chapter 10. And these are hypothesis tests when we are looking at the relationship between some measure of interest in two populations. So I'm going to go through, kind of work through the chapter and what we have in the book. Uh, anyway, so what we have is number one, the process of doing a hypothesis test is pretty much the same no matter what kind of hypothesis test you're doing. Last week, you'll remember that what we were doing is we had a single population and we had some measure we thought existed in that population. We took a sample to see if that measure was different or if it was greater or smaller than what we thought was there initially. And then we made an inference back to our population based on what we found about this measure. In comparing two hypotheses or two sample tests for two populations, what we're doing is we have two populations and we have some measure of interest and we look at the relationship between those. In other words, is one larger than the other or are they different from each other? And we take two samples from these two populations. We then compare the measures between the two samples and we make an inference back to our population relationship based on what we found from our samples. So it's different, but it's easier in some ways. The hypothesis forms, for instance, in these two sample tests have no numbers in them. You're just looking at the relationship. So, for instance, for a mean, you might ask whether the population is different, whether they're different from each other, or whether the means one is less than or greater than the other. So those are the forms that you can have, and you're just basically going to assign those. An example might be, suppose we have students at North Carolina A&T in population 1, we have students at UNCG in population 2, and we do a simple survey and we ask them about their satisfaction levels with parking on campus. So in our first, we get a measure from UNCG in our second sample, and we compare those. Now, our hypothesis could have been, the parking, the satisfaction with parking is different at A&T and UNCG. It might have been that the parking satisfaction at A&T is greater than it is at UNCG, which would have been this third choice here. Or it might have been that the satisfaction with parking at A&T was less than it is at UNCG, which is this middle choice. Anyway, so it's just a matter of figuring out, what the relationship is and then writing the correct form of the hypotheses. So no numbers. A couple of thoughts before we kind of get started on this. If we're looking at the mean, and that's what we look at first. In the book, he uses a test called a pooled variance t-test, which assumes that your populations have equal variances. I'm really uncomfortable with that unless you do an f-test for equal variances to determine that they actually are not different to begin with. So I think if you're going to use the pooled variance t-test, you have to do the f-test for equal variances first. Since we're doing all this in PhStat, that takes about two minutes. Okay, so not very long to do. If I didn't want to do this two-stage thing and explain that to someone, then I had to do two steps. I think I would just play it safe and I would do something called a separate variance t-test. This test does not assume that the variances in the population are equal, so it's a more conservative test. And the p-values that you get from these are slightly higher. So for the first example we're going to look at, I think the p-value, if we use a pooled variance t-test, is 3.71%, and the p-value, if we use this separate variance t-test, is 3.98%. So a little bit different, but I would rather be a little more conservative and do it using the separate variance t-test. So that's what I'm going to show you. You can check the calculations in the book we're at the point where our calculations are getting much bigger. We're looking at computing degrees of freedom that are fairly complicated in our hypothesis test. Students make lots of mistakes doing these things. So we're going to use PHStat to do all of our calculations with. So really there are no calculations in this chapter. Anyway, so our first example, example 10.1, which is on page 312 in your book. In 10.1, we have a research question as to whether the average delivery time from the local pizza restaurant is less than the delivery time for the national chain. Now, you automatically know this is a one-tailed test, and assuming that our local pizza restaurant is the first sample, the mu1 population, we would write our alternative population as mu1 is less than mu2. Delivery time for the local restaurant is less than the chain. And our null hypothesis is mu1 is greater than or equal to mu2. Our PHStat output, the way that we get this is we go to Excel, and this file is called Pizza Time. I'm going to open that up. I've already got PHStat up and working. So I'm going to open, and I've already been here, so I kind of am in the right directory to get this. But anyway, Pizza Time, you'll have to find it. It's in your files. When you open Pizza Time up, you'll see that it's a very simple little file. You've got only a sample size of 10. So 10 times we have ordered pizza from both the local restaurant and the chain restaurant, I assume at the same time, to the same delivery location. And we have computed the times it took to get that delivery in this file. So go to PHStat, and we did one sample test last week. This week we're doing 2 sample tests, and we have 2 choices here. First choice is unsummarized data, which is what we actually have in this instance. We've got the raw data. We haven't done anything to compute a mean and a standard deviation or variance for this data. So that's what we would choose. If you've already computed the mean and the standard deviation, then you would use summarized data. The tests are the same under them though. And again, you open up unsummarized data, it's 2 sample tests, and you'll see that you've got a choice between pool variance t-test, sample variance t-test, and you want the separate variance t-test. When you open it up, you'll see something that looks like this dialog box. The hypothesized difference, unless you have some burning reason to put something else in there, you're always going to put a 0 in here. We're just looking to see if there's a difference, a significant difference at the 0.05 level of significance. We're not saying there's a particular size difference between them. So our population 1, our local restaurant, is our first sample. And the data from our chain restaurant delivery times is our second sample. Put that in. I did select the labels. This is because our hypothesis was that mu1 is less than mu2, a lower tail test. So you have to remember that. And you then say, okay, and you get lots of calculations. But the thing that we, of course, are interested in, number one, there's some information at the top for both of our population samples. So if the one from our local restaurant had an average delivery time of 16.7 minutes, the average delivery time for the chain restaurants was 18.88 minutes, which certainly is a different number, but the question is it significantly different? When you look down at the bottom, again, what we're interested in our t-test is our p-value. And according to our p-value, it's 0.0603. And what that tells us is that we cannot reject the null hypothesis. We can't say that that mu1 is not greater than or equal to mu2. So although there's a difference, it looks like it's a pretty good size difference. It's not significant at the 0.05 level, and we get a p-value that's greater than our alpha level. So that's how you do those kinds of hypothesis tests. and that's how you explain them. And of course, I'm more concerned that you can explain this to your boss or to me than that you can tell me that the p-value is 0.0603 or that you can do the calculations by hand. The next thing we're going to look at in this chapter, so that's one kind of test. The next thing we're going to look at is something called a paired t-test. A paired t-test, or he calls them match samples, I think, in the book also. They talk about two related populations. What this is usually a test that's conducted in some kind of a controlled setting, like an experiment. The researcher gets to choose the sample size, and he gets to choose the order in which the tests are done. So big advantage of this kind of test, other than the control, is the fact that you have very, very small sample sizes. 5 or 6 is big enough. So for instance, suppose we had a manufacturing operation and we have 2 methods of assembling something, method 1 and method 2. We would pick 5 individuals. I would put half of them, approximately half, maybe 3 of them, have the first 3 of them do method 1 first, and the last 2 people do method 2 first. And then I would switch them off and have each of them do the other method. You want to switch them. You don't want to have everybody do method 1 first and then method 2 in case there's some kind of learning that occurs here that would increase maybe the second method if you did method 1 first. So what you're looking at here is not the average of the times, which is what you would have looked at in a regular t-test. You're then setting these up and you're saying, well, what's the difference? Computing all the differences, and you're looking at the mean of the differences, the mu sub d, mean of the differences. The forms of the hypothesis are the same. They work the same way, but you can see it's the mu sub d has to go in here as a measure. And this is the only one that's got a number, and we always have a 0 out on the end. So example shown in the book, table 10, or in table 10.4 on page 320 is a situation where we have textbooks, and these textbooks can either be bought at the bookstore or bought online. They got the individual, so the observations are the actual names of the books, and then we check this difference, and we just want to know, are the prices different? So it's mu sub d is equals not equals is a two-tailed test. So in my paired t-test, when I get my result back, I have something that looks like this output. And the way that I got that was, I go back to my book 1. This is in a file called book prices. So I open up book prices. I'm just going to open it there. Here's my raw data. I've got 16 different textbooks, everything from microeconomics to American government. And I've got the bookstore price and I've got the online price. And I want to know, again, research question, are they significantly different? So is the mu sub d equal to 0 or not equal to 0? So I go to PHStat, 2 sample sets tests, and this is, again, unsummarized data. I go down to paired t-test, and my hypothesized mean difference will always be 0. And I put in my population 1, which is the bookstore, and 2 is the online. Oh, okay, I messed up. 1 is the bookstore, and 2 is the online. And this is a two-tailed test, and I say, okay, and here's my output. Turns out they are significantly different. And of course, this is backed up by the fact if you look at, you look at the D-bar, it's $42 different on average. But anyway, I get a p-value of 0.0014, which is very small, and I know because I got that p-value that I can reject my null hypothesis. So you would explain to your boss that the prices at the bookstore and online are significantly different from each other. So that's the paired t-test. It's very powerful, something that we use fairly often. And anyway, in I don't know what I did there. Anyway, something that we use very often. A third kind of test that you might see in this chapter is where you're comparing the proportions of two populations. So instead of the mean as a measure, we now have the proportion, which again is denoted with this pi symbol. And so pi 1 equals pi 2, and so forth. So that same things, not equal, one smaller, one's greater, and that's why you set it up. In this data, in example 10.3, on page 329, we have a research question as to whether the proportion of men who use Facebook to share with many people at once is less than the proportion of women who use Facebook to share with many people at once. And instead of giving us the actual data, they give us summarized data, so we don't have to go compute the proportions. They tell us that the X is 193 out of a sample size of 459 for the men, and 250 of the women did that out of a sample of 501. So when I write because my research question said, is proportion of men greater, assuming that men are my first population, less than. My null hypothesis is that it's greater than or equal to mu2, and my alternative, which goes to my research question, the men have a smaller proportion than the women. To do this in PHStat, you would go back to PHStat or the Excel, choose the two sample test, but now we want the summarized data, because this data is summarized for us, and this is the z-test for differences in two proportions, and it's, it wants us to actually put the data in because I told it summarized. Again, our hypothesized difference is 0. Number of population 1, which is our men, has a X value of 193. It has a sample size of 459. The women that we sampled, 250 of them said that they use Facebook to share with lots of people, and 501 was our sample size. And this was a lower tail test because we summarized that the proportion of the men was smaller than the proportion of the women. And I say, okay. And this is my PHStat output. So here's my z-test for the proportion, and it turns out that my p-value is 0.0074, which is considerably less than my 0.05, so I would reject the null hypothesis for this. Anyway, which means, and again, if you had to explain this to your boss who says, are the men really lower than the women for sharing lots of things, we would say, yes, the proportion of the men who use Facebook to share data to many friends is significantly smaller than the proportion of women. Anyway, that's our proportion test. And there, just the output. And then the last thing that he puts in this chapter is this F-test to determine whether the variances are different. So sometimes a researcher might really be more interested in the variability of a process or population rather than in the central tendency. So this test is the one that's used as a pretest to determine whether the population variances are different, so that you can use a pooled variance t-test if you want to use that instead of a separate variance t-test. So the form of the measure is always the same as it was just you're checking a variance instead of a mean or a proportion. Um, and the book says, and we'll stick with this because I think they do this for calculation purposes and using an F distribution, but the sample with the largest standard deviation should be the first sample. I do not know why, but that's what the rule kind of is here. So example 10.4 on page 334. We have a data from waiting times at a restaurant, and they are interested in the variability of this waiting time. And they want to know whether there's more variability in the waiting times at lunch, our first population, than at breakfast, which is our second. And they put them in that order because the sample variance and the standard deviation is larger at lunch than it is at breakfast. Again, that's purely a calculation thing, but that's okay. So since we asked whether it was larger at lunch than at breakfast, our hypothesis forms are the ones that I've got here. So our HO is that mu1, the variance in the population 1 is less than or equal to variance in population 2. And our null hypothesis is that the variance in population 1 is greater than population 2. I'm sorry about the howling dog in the background. So what we do is we go back to Excel, and I'm just going to open up another sheet. I'm going to browse, and this data is for this is actually in not in a file. It's this. So that's wrong. I'm just going to open a new file. Is this summarized data also? You can use summarized or unsummarized. In this case, we do not have the initial data. So what we do is we go to phstat, pick off 2 samples, summarize data, and this is my F test for differences in 2 variances. And my level of significance is 0.05. You didn't change that. So for my first population, which is lunchtime, we have a variance, a sample size, I'm sorry, of 25 and a variance of 4.4 minutes. At breakfast, we have a sample size of 21 and a variance of 1.9 minutes. And this is a upper tail test. That's why they tell you to do that in phstat, I guess. It's set up that way. And we say, okay. So here are our calculations. Our F test comes back that our p-value is 0.0303, which is less than 0.05. So our statistical decision is based on these samples that we can reject the null hypothesis that says that the variability of the wait times at lunch is not less than the ones at breakfast. In other words, there is it's significantly smaller or larger. I'm sorry, lunch is significantly larger than at breakfast, the variability. And again, your boss wants to know which one has more variability. You know, is it really more variable at lunch than it is at breakfast? And you would tell him, yes, based on this hypothesis test, the variability is actually greater. Anyway, that's chapter 10. Hope that helps some. I did put the notes up, and just let me know what you need. Thank you.